Welcome to the lesson video on boosting. In this video, we're going to talk about boosting, which is a method for creating tree ensembles, or generally any predictor ensembles, in which the predictors are created sequentially, in which each new predictor is trained to correctly predict samples that the previous predictors got wrong. So we're going to talk in detail about ways to do this in this presentation. There are a number of different ways it can be done. This, particularly when applied to trees, it allows us to build an ensemble with a flexibility of trees, but the method of training eliminates a lot of the errors, and so we wind up with a high accuracy ensembles. In fact, many of the top performing prediction methods are based on boosting classifiers using trees. So here is a recipe or an algorithm description for doing gradient boosting with regression. Gradient boosting is one of the most powerful methods for boosting. So step one is just fitting regression tree. So we're going to fit this regression tree. We're going to call it f hat, and we're also going to call it f with a superscript 0, and just fit a regression tree to our data. Fairly straightforward. Sometimes this regression tree will be restricted on size, because when you're doing boosting, usually you want what are called weak learners. You want your individual learners or your individual prediction algorithms in your ensemble to not overtrain, want them to be weak. And so step two is going to be to iterate through these three steps, and we're going to iterate for little b equals 1 through b. So little b would just be an indexing variable on the tree, so we're going to build a bunch of trees, and capital B is going to tell us how many trees we're going to build. So each time we go through these three steps, we're going to build another tree that we're going to add to our ensemble. So the first thing we do is we compute the residuals, which are Ri. So for each I, Ri is going to be Yi minus f of Xi. That should be an I. And so Ri is going to be the error. We call it the residuals, but it's the error for the ith data point based on the current ensemble f hat. And then we're going to train a new tree. Once we have those errors, we're going to new tree, which is going to be FB. It's going to be the next tree in our ensemble. We're going to train it on the residuals, and that means that we treat the RIs as our new Y values for our data. And so that creates our new tree FB, and then we're going to add that to our ensemble, and that's what we do. In the next step, F hat, we update the ensemble. It's the previous F hat plus lambda times FB. So we've added this new tree FB to our ensemble, but sitting in front of it is this lambda, and we're doing regression here. And so what this lambda does is it's a learning rate. So we don't want to add the full FB. FB has learned our errors, and if we just added FB in there, we'd wind up overtraining. So that lambda slows us down. It slows down our learning, so we don't wind up overtraining. And then we've updated this f hat, that's our ensemble at each step, and then that f hat in the end is our ensemble. That's our gradient boosting tree ensemble. Okay, so a couple of comments. Usually the trees are restricted to some maximum number of terminal nodes. So as we mentioned, it could be just 2 nodes, like 1 decision, 1 split, and then 2 nodes, or it could be 12, 32. Those are fairly common types of numbers you would use. Lambda is called the learning rate. As we've mentioned, it controls how quickly the ensemble changes based on learning the residuals. Okay, so let's walk through an example. This is kind of a cartoon example, but it gives us a good feeling for how this works. So it'll build some good intuition through this cartoon example. It's don't take it too literally, but it'll help us to understand kind of pictorially how gradient boosting works. So I have my data here. We have y as a function of x. We're doing regression. I've tracked individual data points, but I drew it as a curve so it would be easier to see, which makes my little data points be little boxes. So the first thing we do is we fit a regression tree to this data. We're going to assume it's a very simple regression tree, so the regression tree just gives us a function that looks like a box, right? It's 0, and then it has some value up here, and then once you hit above that threshold, it goes back down to 0. And so that's going to be our initial simple kind of weak learner regression tree. Then what we're going to do is we're going to compute the residuals. So the residual here, Ri is Yi minus Fi. So yi minus fi would be that amount right there, which gives us the height of our residual. So we take the curve in the top, we subtract off the box, and we get this chopped up curve in the bottom, and those are our errors. Then we're going to make a new tree, FB, that is going to be trained on those residuals. So this FB is F1, we're in our first iteration. It's trained to learn the residual. And so you can see that F1 has learned in a fairly weak way what that residual looks like. We take the F1 and we add it. So we take F1, we multiply it by lambda, and then we add it to the F. And so that's giving us this sort of small top hat type box. So if we go a step before, right, you look here, we just have the box as F. And then in the next step, we've gone back to the slide with step 3, and now we've added F1 on top of F, and now this is our new F. Then we'll go to the next step. The next step is, because we're repeating steps, these 1, 2, 3 steps, we can recompute the residuals, and so you see down here, we've recomputed those residuals based on the new F hat, and we repeat that we're going to retrain on these new residuals and over again, and then you look up here at this F hat in the plot on the top, and F hat has a function with lots of little tiny steps. And so it's learned the contours for our X and Y data. And so that is a good feeling for how gradient boosting works for regression. It works similarly for classification, as we've seen a couple of different times. The way you check things and your criteria and how you compute your residuals are going to be a little different, but at least philosophically and the basic structure is very similar to this for classification. So as we mentioned, usually the trees are restricted to some maximum number of terminal nodes. That makes the individual trees what we call weak learners. And then once we make a bunch of weak learners, this process of boosting reduces the bias error. Those weak learners have put a sort of a strong assumption or a strong bias on what the structure of the relationship between X and Y is. And then by learning our errors in this process of boosting, we reduce that bias error. Also, lambda, it's right there. Lambda is called the learning rate. And here's what happens if lambda is too high or too low. If it's too low, we're going to need a lot of trees because each new tree isn't going to update our ensemble very much. We're going to need a lot of trees to learn the contours. If it's too high, we'll get overtraining. Right? We're going to learn those residuals, those errors too quickly, and we're going to overtrain to the specifics of our current data. Typically, you pick a lambda in 0.01 or 0.001, and then you might modify it by cross-validation. Okay, so Adaboost is a boosting method for it's an early boosting method, and it's useful in computer vision. And in Adaboost, we're going to use the same philosophy where we build a sequence of new trees one at a time, and each new tree is going to be trained to do well on the errors from the previous trees. So let's start with the original data, and we're going to kind of walk through an example step at a time. And so there's our original data, red pluses for one class, blue minuses for the other class. And so we built our first classifier in this data set. So the first classifier, in this case with Adaboost, it's always one threshold, 2 branches, 2 terminal nodes. So we've picked the one threshold, or the optimization method picks one threshold, put it right there. Everything above that gets called blue class, everything below gets called red. Now we've circled the data points that were incorrectly classified, and so we want the next classifier to be correct on those, or to try to be correct on those, to care the most about those. And so what we do is we add a weight to those. We're going to increase those by some weight. I've indicated the weight by making the font a little bigger and putting some circles, but there's some formula that tells you how much you would want to weight those greater. Now we build our next classifier. We're going to train it to this data set, but it's going to have those weights on the data that tell it what it wants to classify correctly. And so it'll put greater burden on trying to classify correctly the things that were classified poorly before. And you can see a vertical split, and this vertical split makes a lot of sense. We've now classified all 3 points that we poorly classified before. We've classified all the red points well, but now we have these 3 blue points that we've circled that are now incorrect. So those are going to get greater weight in the next classification. And so this is the second iteration here. Everything with a circle has been misclassified once. And so it's going to put a little more weight on trying to classify those that were misclassified before. And so here's where our next threshold would be. So threshold on the horizontal axis, everything to the left blue, everything to the right red. And then our final Adaboost classifier here using these 3 trees would look like this. And you can see it's now correctly classifying everything. We've taken these 3 trees and just overlaid them. Everything in this region has been labeled red 3 times. Everything in this box here has been labeled blue once and red twice. Everything here has been labeled blue once and red twice. So the split or decision surface separates our 2 classes according to the prediction. It's going to look exactly like that. And you can see the accuracy would be perfect in this example. So this is a good example that shows how these iteration and these changing the weights on the data points when they're misclassified leads to an accurate classifier where it's nonlinear and higher accuracy built on these weak learners, which is a good example of exactly how Adaboost works and a general idea with boosting. Here's a recipe for Adaboost, and it fits what we were just describing. The thing that's in here are all these formulas. Here's the new weight, and it's the previous weight times this term, which is just going to reweight the data points depending on how often they've been misclassified. So here's a plot that shows a method for choosing the tree depth and the number of trees. And so this is typically how you choose a number of trees, similar to what we've talked about in random forest. You want to plot some error as a function of tree, and then you follow your curves, and where they flatten out, that's where you're going to pick your number of trees. But here we're showing these plots for 3 different parameter, well, 2 parameter values for boosting, and then including a plot for random forest. So let's look at on the plot, look at the graphs, the curves that are plotted. The first one here is in green, that's the highest error, and that comes from the random forest. So we see that out of these 3, the one that's doing the poorest is random forest, which is a good statement for boosting that it can beat random forest. Random forest is a good method. The blue, the next highest, that's boosting with depth 2. So that's a slightly larger tree than boosting with depth 1, which is the highest, and that's giving us the lowest error. So we see in this example, boosting with a smaller tree or a weaker learner is doing the best. So let's review what we've talked about today. Boosting is a method for building an ensemble where predictors are built sequentially, and each new predictor attempts to correctly classify or predict regression values for things that were wrong by the previous predictors. And there are some variations on how this can be done. These ensembles have the flexibility of tree ensembles, but they're trained to eliminate the errors, which gives a high accuracy or low error. And many of the top performing prediction models are using gradient boosting trees, and that's especially true for categorical data. Thank you very much for watching.